Rayleigh Ritz method is the basic equations that we need. Is the same as what we have covered in the EAS661, but the basic idea behind why we can use Rayleigh Ritz method to determine P critical, I will make it clear to you, but the equations that we need to make use of will be the same as EAS, what we cover in EAS661. We need to make use of, we need to evaluate the strain energy. Because we need to evaluate the strain energy due to bending, because when we want to determine critical load, we assume that the member will bend. Okay, we assume the member will bend, and because the member bends, so there is strain energy involved, which is strain energy for bending. The second thing is we are going to use the principle of stationary potential energy. In EAS661, we call it principle of minimum potential energy. So we are going to use that principle, but we call it here in the more general case, which is principle of stationary potential energy. And we need to evaluate the total potential energy. So total potential energy, if you can recall, it is a summation of strain energy plus potential energy of external load. So here the external load, later we are going to look at, is the axial load. So we need to find the total potential, the potential energy of the external load, which is the axial load. And when we add them up together, we have the total potential energy. Then we apply the principle of stationary potential energy. We come up with the equation of equilibrium. And from that equation of equilibrium, which we establish for the slightly bent configurations, then we can apply the conditions of non-trivial solutions again to determine the P critical. So that is the basic flow of this method. And as I shown on this slide class, you can refer to section 2.6 and section 2.7 of the book by Charges, page 94 to 103. Okay? It covers 2.6 and 2.7. And also on section 18.6 on the lecture note that is called structural instability, or in page 627 to 61. So these two gives an explanation about Rayleigh Ritz method. And for stiffness matrix method that we are going to look at the next lecture, you can refer to section 2.14 of the book by Charges, or page 133 to 142. Now let me start with Rayleigh Ritz method first. Okay. Now Rayleigh Ritz method is an energy method class. So energy principle is being used to determine critical load. We use that to determine critical load of a member. And we make use of the theorem of stationary potential energy. Okay. Now here I have added these two points here, which is not in the notes that I shared originally with you. So basically in Rayleigh Ritz method, as you can relate to Rayleigh Ritz method that we cover in EAS661, we have to make assumptions about the displacement field. So far, when we determine P critical, we don't make any assumptions about the buckling shape, or what we call the slightly bent configurations. So we derive equations, okay, and we make use of the method like slope detection equation method to determine P critical. So, but we don't make any assumptions about the displacement field. But in Rayleigh Ritz method, we make assumptions about the displacement field. The displacement field for what? For the slightly bent configurations, which means if it is going to buckle, okay, it's going to buckle. So what is the buckle shape? We make assumption of that in Rayleigh Ritz method. Okay, so this assumption that we make is for the displacement field of the slightly bent configurations, which is possible at the state of neutral equilibrium. Then, with this assumption of displacement field, we apply the principle of stationary potential energy to come up with an equations, okay, to determine P critical. So when we use that equations, we apply the conditions of non-trivial solutions. And from that equations that we obtain by applying principle of stationary potential energy, we obtain the P critical. So this is a basic idea. So we have to make assumptions of the displacement field for the slightly bent configurations. So because we make assumptions, so this is just an approximate method, because it depends on how accurate, how good is our assumptions. And later we will see example, we can improve further the assumption that we make by making other assumptions of the displacement field, for example, by adding more terms to the displacement field, similar to what we have done in this EAS661. Okay, so this is to give you all some basic idea involved. So in Rayleigh Ritz method, this slide also I will share with you as an additional slide later on the e-learning. This is not in your lecture notes. Originally I shared. So in Rayleigh Ritz method, we need to make use of this. We need to calculate these two things. The first thing is strain energy due to bending, which is, you are familiar with this, is integration from 0 to L half EI d2V dx2 square. And we need to calculate also the potential energy due to axial load P. When we apply Rayleigh Ritz method, the load that is applied on the member is axial load. It's not the same as when we look at Rayleigh Ritz method in EAS661, we have a load which is causing the member to bend. In the problems that we want to solve using Rayleigh Ritz method, the load which is acting on the member is the axial load. And then we have to find the potential energy due to axial load, which is given by these equations. V negative, so always potential energy, there's a negative P over 2, integration 0 to L, dV dx squared. And V here is the assumed displacement field of the slightly bent configuration at neutral equilibrium. Okay. Now this one we already seen how we get this. Now we are going to go to this part. How do we get this here first? Okay. Now let me go to this particular part here, just to let you know where you can find this. This is in page 94, section 2.6, Rayleigh Ritz method. So some preliminary explanations, initial introduction. So what Rayleigh Ritz method, why is it useful, and then what is the advantage of this? So next it gives an example. Okay, so we will come back to this example. Okay. Now what I want to point out is how to get this equation. And how do we get this equation? We will start with some explanation of where this equation comes from. You have to remember these equations. Okay, this is for applying Rayleigh Ritz method to determine P critical, and it is given by this equation, negative P, this is the axial load applied over 2 integrations dV dx squared. Okay. Now these equations, where does this equation come from is explained here. Okay, so this is another note that I share very early on with you that I refer to from time to time for this EAS663 together with the book by Charges. This is on section 18.6, energy method for the calculations of buckling loads in column. Okay. So here it also shows the strain energy equations, which is needed when we want to use Rayleigh Ritz method. And note that the x which is being used in our lecture note to represent the actual coordinate is is replaced with z here. So z is being used here. So x and z is the same in so d2v dz2 is the same as d2v dx2 that I use in my lecture note. Now the potential energy V of the buckling loads referred to the straight position of the column as datum is given by this equation. Okay. Now this buckling load, this potential energy of this axial load P, we refer to this diagram class. So this is the load acting on the member, and because the member will bend, okay, the member will bend at the point of neutral equilibrium, it will bend into these slightly bent configurations. So when it bends, so originally the axial force acting here, when it bends, so this axial force will move a distance equal to delta. So this is a point load. The total potential energy of point load is negative P, the load itself, multiplied with the distance it travels in the same direction of the load. So this is similar to what we have seen in EAS663. Potential energy of a point load is equal to negative the load itself multiplied the distance the load travel in the direction of that load. Now we want to show that delta is actually what delta is. Okay, what delta is and how do we evaluate delta. Now referring to this diagram here, so this is the originally the member is straight, the length is L. Okay. The straight member, the length is L, then it bends into this shape. Okay, so in the x-axis direction now, or z-axis direction now, if we measure here, the length become L prime. That is, the length become L prime. But the bend length here, is remain the same. Okay. The bend length here remain the same. So this is the assumption that we make. It will bend into this bend shape, but the total bend length is the same. So this, you see the length L is still equal to L. But if we measure along the z-axis direction, so the length become reduced because of this movement delta. Then we would like to next move to this derivation. If you look at this, okay, so we look at the small length here. The small length here along these bend configurations, and we first we find an equation representing this length. Take note, this is the z-axis and this is the y-axis. So this is a small length, differential length, delta L. So that delta L is equal to this, a small delta z square plus delta v square. So delta z is a very small length here, square plus delta v square. So is equal to delta L square. This is just assuming that they are straight line. Is using this Pythagoras theorem, so we can get this. And the square root of that gives us the length delta L. Okay. And if you take, if assume that the slope is very small, and if the slope is very small, which is dv dx, dv dz is the slope. This is a slope. This is just slightly bent. Okay, so slightly bent. So the slope is small. Then we can represent delta L using these approximate equations. Okay. We can use this using these approximate equations by having this assumption dv dx or dv dz here is small. Now remember, this delta L class is a small length of this bend configuration. So if we integrate from 0 to here, then we will get the total length, which is equal to L. So this is the next step, which is being done here. Integrate all the small length, okay, from 0 to L prime first. We substitute here, then we get this. So this one, we can rewrite this. This is 0 to L prime, there's a 1 here, so we can rewrite this into L prime plus integration 0 to L prime half dv dz square. So delta that we are interested to know is therefore given by these equations. And this multiplied with P and put a negative in front give us the potential energy of the axial force. Now, here we are looking at, let me go back to this diagram here. We are looking at a very slightly bent configuration. So this one actually, it moves, this one actually, L and L prime, they are approximately equal because we are looking at very slightly bent configurations. They are actually not the same, but because they are slightly bent configurations, so this L and L prime can be considered to be approximately equal. Okay. So from here, we represent this approximately as this. So L prime is replaced with L here. Okay. So finally, we get delta is this. And when this delta multiplied with negative P, that gives us the potential energy of the external load, which is axial force here. So these equations is the equations that you need to remember together with the equation for bending, with the strain energy for bending. The strain energy for bending will be given by this equation that we use, or it can also be expressed in bending moment using these equations. So, but we will use these equations. So, total potential energy is the strain energy due to bending plus the potential energy due to external load, which is due to axial load, which is given by these terms here. So this and these terms that is the expressions that you have to remember if you're asked to use Rayleigh Ritz method to solve for P critical. So now, after showing you how to get these equations, let me come back to this particular slide. So again, just to refresh, you have to calculate this and you have to calculate this. And to calculate this, we need to first assume what is this, and then make the necessary differentiations, and then square, and then integrations. The same thing here, make the necessary differentiations, and then square, and then integrate. So there's a lot of differentiations and integration to be done, so we must be familiar again, like in EAS661, how to differentiate certain functions and how to integrate them. Now, let me use this particular example, I think just to briefly go through with you the process. Okay, and this example is given actually here in this section 2.6. The detail of this is given here. So I just summarize that, the main equations, and you can refer back again to all these detailed explanation steps about the process of solving this problem. A cantilever of fixed free column, what is the P critical? So this one, we know the solution. Okay, from Euler theory, we know the solution. Then we can try to compare what is the accuracy of Rayleigh Ritz method and what is the factor affecting the accuracy. So the first thing that we do here is we have to assume this slightly bent configuration. At the state of neutral equilibrium, we have this straight one and this bent one possible. So in Rayleigh Ritz method, we have to first make assumption about this slightly bent configurations. That means if at the state of neutral equilibrium, this column can stay in the straight configuration and can stay in the slightly bent configuration. And what is the shape of this slightly bent configuration is the first thing that we have to assume. So assume deflected shape of slightly bent configuration. So we assume two quadratic terms first. This is up to us. We can put sine for sine, but it has from the conditions of boundary conditions, which is here, y must be 0 and rotation must be 0. So if apply that two conditions here, so A and B become 0. And The only terms that remains is this. So this also must be also kinematically admissible, which is the same thing, same requirements for EAS661 that we have gone through for Rayleigh Ritz method. That means it must satisfy the kinematic boundary conditions. Okay. So next, after we decide on the assumed reflected shape of these slightly bent configurations, then we obtain the strain energy due to bending. So remember, what is that? Then we obtain the potential energy due to axial force. Here, remember the equations. And by substituting this into the equation for these and these, differentiate first and then integrate. Then finally, we get to this. So in these equations, we see that the C, which is unknown here, appear, as well as the P. This is the P critical that we want to obtain here, appear in this equation. Then this is where we apply the principle of stationary potential energy, which is the variation of potential energy must be zero at the positions of equilibrium. So this means that the same thing in what we have seen in 661 means that this differentiate the total potential energy with respect to the unknown degrees of freedom here must be equal to zero. So there's only one here, so we have only one equation. If there are two unknown here, then we have two equations that you need to solve. Then if we substitute this and this here, just differentiate, then we can get it simply, we can get it very, very easily to these equations. So again, these equations appear many, many times. I think in the topics of stability of structures, you get to this equation, which is like an eigenvalue problems, where you need to decide the solution that you want here is a non-trivial solution. So this multiplied with this equal to zero. So non-trivial one is the solutions of P that will make C non-zero possible. So in order to make C non-zero possible, this one must be zero. So that is the condition that we use here in order to get the P critical, which is a bit hidden here. So P critical will be 3EI over L squared. 3EI over L squared. So this is the approximate P critical that we get using Rayleigh Ritz method with this assumption. C is equal to Y is equal to CX squared. Now, if you compare, okay, if I come back to this here, okay. I'm going to go to the next page. Okay. So this is a solution process. So this 3EI over L squared, equation 2.46, if you compare with the exact buckling load, so this is a good thing when we use the problems that we know. Of course, we just want to show to you, Rayleigh Ritz method gives you just approximate solution. So the exact buckling load is pi square EI over 4L squared. We know this from the Euler theory. So if you compare this with this, the error is 21.6%. Okay. The error is become 21.6%. 3EI over L squared, this is pi square EI over 4L squared. Okay. And this is pi square EI over 4L squared is actually 2.46. 2.46 EI over L squared. So you compare with this is higher than the exact one by 21.6%. Higher. Okay. Higher. Now, as in the case of EAS661, you can further trying to improve the accuracy by making it by adding another terms here, which is we stop just now we use x squared. If you put another terms x cubed here, then do the same thing. Now you have two unknowns. Now do the same thing. The equation become more lengthy now. So add up the potential energy. The total potential energy has C and D as well as P inside the equations. apply the conditions of stationary potential energy, which means you have to two unknowns now. You have to get these two equations by carrying out these partial differentiations. Then we get to these two equations. This one, 2.52 and 2.53. So what do we do next? Remember, what we want to solve is for P, to make the non-trivial solution possible. So we rearrange these equations because this is quite a complicated, not a complicated, a lengthy equation. So to simplify that, okay, we just introduce some additional expressions here, alpha PL square over EI, to make this a bit neat, a bit more simplified. Okay, but remember alpha is PL square over EI. And these two equations is arranged in such a way that you have something multiplied with C plus something multiplied with D, first equations, something multiplied with C plus something multiplied with D, second equations. And this something here include P inside here, which is embedded in alpha. So there's something which is a function of P, function of P, function of P, function of P, multiplied with the unknown coefficients C and D, which we assume in the displacement field. Okay. So in order to get non-trivial solutions, which is we want to find the value of P, which is going to make C and D non-zero. So the condition is the determinant of this matrix must be equal to 0 of this matrix. So this is being explained here. So the determinant, this is a symbol for determinant, must be equal to 0. And this is the equation to be solved. So there are two solutions. So we look for the lowest one, the lowest and the non-zero one. There are two solutions here. Alpha square, so there are two solutions, these quadratic equations. We look for the non-zero and the lowest one, okay? And the solution for this we obtain from here is 2.49. 2.49, okay? So P critical is 2.49 EI over L square. So, and we compare with the exact one, which is 2.46. So this is higher than the exact one by only about 1%. So by adding a term which is cubic, we have improved the accuracy very much in this case. Okay. But there is a remark here. A very significant increase in accuracy from 21% to only 1% difference has been achieved by just increasing the number of terms in the assumed displacement functions. So this is so happened applied to this case, okay? But the rate at which the solution usually converges to the exact answer should not be expected to be as rapid as was the case here. Okay? It so happened in this case by adding one more terms, the accuracy improved a lot, almost the same. But in general, this will not be the case. That you add one more terms, you get very good accuracy. Okay? In general, the more complicated the deflection shape, because it depends on the deflection shape. In this case, it is not that complicated. This is a cantilever column, not complicated. That's why the accuracy improved very fast. In general, the more complicated the deflection shape, the more parameters are needed to obtain a very accurate result. Okay. Now, this is an example, okay, of how we apply Rayleigh Ritz method and how we can further improve the accuracy by improving the assumption that we make, that is by adding more terms, okay? And all the terms that we add must eventually satisfy the conditions of, it must be kinematically admissible, which means the geometric boundary condition must be satisfied. Now, This is another example of applications of Rayleigh Ritz method. Okay, so the process is similar. Only thing here is when we do the integrations to get strain energy, we must be careful that because the I is changing. The I is changing. So we must integrate it part by part. So integrate for this part first with this I value, and then integrate for this part with this I value, and then integrate for this part with this I value. So this is a step column where the I is changing. So when the I is changing, because our strain energy has I in the equations, so we have to divide this integration into this integration, this part, plus integration for this part, plus integration for this part here. That is for strain energy. But for potential energy of external load, because it does not concern with EI, so you can integrate. You can integrate all, or you can, because since you want to, for EI already, for strain energy already integrate part by parts here, then we can also do this part by part. But we do this part by part mainly for the strain energy because the I is different for different parts. So this is an example which is also given in the book by charges. After this, we go through briefly the solution process. So let me first explain what happened there. Is first we assume for the slightly bent shape, this column at neutral equilibrium is going to bend into slightly bent shape. And that shape that we assume here, we start with a sine curve. Only one term here, A sine pi x over L, only one term here. Okay. Then we go through the process of using Rayleigh Ritz method, and we found that P critical is this 0.864 pi square EI over L squared. Next, we add one more terms, okay, to this problem by trying to improve the accuracy of P critical that we can get. We add one more terms here, which is plus B sine 3 pi x over L. Then we obtain the P critical to be 0.735 pi square EI over L squared. Now the exact one, I think this one can be solved using the exact procedure, the methods. So the exact one is 0.65 pi square EI over L squared. So if you compare this, and this, so first this approximate one is higher than the exact one. The approximate one is higher than the exact one. And when you add one more terms, so this one compared to this one becomes smaller. And you can expect if you add one more terms here, A sine pi x over L plus B sine 3 pi x over L plus C sine 5 pi x over L, this one is expected to be, the next one, if you add one more terms, will be lower than this, but it will be still higher than this. So what we try to point out from this, and also from the example on the first example, the cantilever column, the critical load that we obtain from Rayleigh Ritz method are approximate values. These are approximate. And the value that we obtain will be always larger than the exact value. This approximate one that we obtain will always be larger. Why? Because the fact it lies is due to the fact that we assume deflected shape. Because we make assumption about the slightly bent configuration. We make assumption that the column will buckle into that shape. That might not be the exact shape, and it depends on how good our assumption. It might be a very bad assumption. So why it is always greater than the exact value is because we make assumption about the deflected shape, And if we make assumption about the deflected shape, we don't let the column deform freely. To get the slightly bent configuration, we make assumption you must deflect like this, meaning that you already give some constraint. You already give some constraint for the column to deflect. So application of constraint in order to force column to take up an artificial shape, because we make assumption of this shape. So the column has to deflect into that shape. So in order for the column to deflect into that shape, so you have already applied some kind of constraint. And because of this constraint, it makes the column stiffer. Okay? So when you make the column stiffer, when we try to relate back, if the column is stiffer in terms of restraint that we provide, which means we don't let it deflect freely, we don't let it rotate freely because of the constraint, so it makes it stiffer. So when you make the column stiffer, which means you increase the restraint, then the P critical will increase. So this is the things that you need to be aware of, okay? But the difference between the approximate values and the exact value can be made smaller if we improve the assumptions of the deflected shape that we use. So this is similar to EAS661. Okay? When we solve our problems, when we try to actually find the deflections, we make assumption first. And if the assumption is good, then we get a good accuracy. But the result that we get for EAS in EAS661, the result that we get, the displacement that we get, will always be smaller than the exact one, because by making assumption about the deflected shape, you already introduce some restraint, and that restraint makes the whole structure stiffer. So when making the structure stiffer here, it causes the critical load to be higher. Okay. So that is the explanation for that. Okay. Now, let me go through this particular solution process briefly. So this is the one example that I showed to you in the slide just now. This is application of Rayleigh Ritz method of column with varying variable cross sections. So class, I think Rayleigh Ritz method is especially useful advantage when we want to apply it to solve a problem where we do not know the exact solutions. If we know the exact solution, there is no point we use Rayleigh Ritz method. So might as well we use other method. But Rayleigh Ritz method is useful when we want to apply it to a problem like this, okay, which is quite difficult to solve for this using the exact method. So we use this approximate method, and we try to improve the accuracy by adding more and more terms in the assumed deflected shape for the slightly bent configurations. So this example, okay, has a variable moment of inertia. L/4 here is IO/4. L/2 here is I subscript 0. And the remaining L/4 is again the same here. So this is symmetry. Okay, symmetry with respect to the center line of this member. So we assume this buckle shape or the slightly bent configurations at the state of neutral equilibrium for this problem, for this column with different moment of inertia along the length to be in the sine curve. First one sine curve, okay? A sine pi x over L. This might not be good, but we make assumption first, start with this, okay, and see what is the P critical that we can get. So this satisfies geometric boundary conditions, okay, zero deflections and non-zero slope at the ends of the member, but this is just to refresh. This does not have to satisfy the natural boundary conditions. Now here we can integrate the whole length of the member, but here we take advantage of the symmetry. we take advantage of the symmetry. So this is 2 times of this. So this we just integrate until half only, until half of it, and then multiply with 2, give us the strain energy for the whole column. So this is the steps involved here. So 0 to L over 4 is the first step of the column, and then 0 to L over 2 to L over 4 to L over 2 only, okay, because we consider only half of the column because of the symmetry. And then this thing multiplied with 2 give us the strain energy of the whole column. Now here, some of the process of differentiation, integration has to be carried out. So it is very useful for us, I think, to try to remember how to differentiate sine, cosine, or sine square, cosine square, and how to integrate sine square, sine, cosine. So those are the things that will have to be evaluated. So we need to know how to do that. So here it is already given here. If you integrate these, what do you get? If you differentiate this second part, what do you get? Okay. Then after that, we get the strain energy to be equal to this. So here you see there is an A appear here, which is the unknown that we assume in the deflected shape. Then the potential energy, remember these equations, and then we do the necessary differentiation, square it, and then integrations. You get to these equations, which is, you see here now, potential energy is a function of P, and there's an A here, and you add them up together, you get this. Next, you apply the principle of stationary potential energy, which means we have to carry out these differentiations of the potential and total potential energy with respect to A. This is unknown coefficient in the deflected shape that we assume. And from here, you get to an equation that you need to use and apply the non-trivial conditions. To get non-trivial means A should be to get solution of P that will make A non-zero. So this should be 0. So from there, we get this P critical. This is what I show you just now. The exact one is this. So the difference is this is higher than this by 33%. Now, if you add one more terms and then do the same thing, now the calculation become more lengthy, but process is still the same. But because you have A and B here, so the equation become more lengthy now, so very lengthy. So you have to differentiate, integrate many things here. So these are just the equations, are just the process to show us. And finally, I need to also get involved in this kind of integration, and then, so if we consider all these, and then we get the total potential energy equal to this. So here we have a function of A and B and also P. Because there are 2 unknown coefficients here in the displacement field, so we need to do partial differentiations. Respect to A, respect to B, get to these 2 equations, which is in terms of A, B, and P. So this is 2 equations, right-hand side 0 with unknown coefficient A and B, which is included in the assumed displacement field. So to get non-trivial solutions, so we first come to these equations. This is just rearranging these equations to get non-trivial solution, which is A and B not equal to 0. So the determinant must be 0. The determinant of this right-hand side of the equation must be 0, which is that means this multiplied with this minus this multiplied with this must be equal to 0. Then we get the quadratic equations, and we can solve for P, and the smaller of these 2 solutions will give us the P critical. And by adding one more terms, we improve the accuracy from 33 to only 13, higher than 13%, from 33% higher than the exact to 13% higher. So that is the process of Rayleigh Ritz method plus And we have to go through the process of using Rayleigh Ritz method. First, choose a assume deflected shape. Choose an deflected shape that will correctly represent the slightly bent configuration. And the first thing, it must be kinematically admissible. It means the geometric boundary condition must be satisfied. Then we evaluate the strain energy. Remember the equation for strain energy. And we evaluate the potential energy of the actual load P. Remember that equation for that. Add them up together to get the total potential energy. Then we apply the principle of stationary potential energy. And we will get an equation. Depending on the assumed displacement field, it has one unknown coefficient or more than one, then the corresponding number of equations will appear. And after we apply the principle of stationary potential energy, we come up with the equations for us to determine the P critical. And we use the criteria that we want to get non-trivial solutions. With that, we can determine the P critical. If there are no more than one solution, we choose the smallest non-zero one to be the solutions. So that is